Simple covalent molecules for GCSE and IGCSE.
Chemistry Explained are chemistry lessons designed for you to participate in. So make sure that you are writing notes and completing tasks on paper or on tablet. Move through the lesson at the pace that suits you. Skip ahead or move back as you wish. Most importantly, when prompted, pause the lesson, complete the task, but taking your time and thinking the problem through. Resume and check and correct your answers before moving on.
So we will start the lesson with a review of chemical bonding, move on to covalent bonding diagrams, simple or small molecular structure. Two terms are used in different specifications, simple and small. I will vary between the two. Molecular properties and then limitations to the covalent model. Check against your specification. You'll see that in this case, AQA, Edexcel and OCRA, as well as IGCSE, will cover all those subtopics. So the first idea to review is that of metals and non-metals. We can see that metals are positioned to the left of the periodic table and non-metals are positioned to the right. So we have grey background for the metals, a beige background for the non-metals. So the two types of element allow for three possible types of combination: metal and non-metal, 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 and of course metal-metal. Pause the lesson and allocate the correct type of bonding to a particular combination. Come back when you are ready to continue. So to resume, we have ionic for metal and non-metal. That's a topic of a separate lesson. Metal and non-metal and non-metal, of course, is covalent, which is the topic of this lesson, and metal is, of course, metallic. So here are some compound names or substance names: magnesium oxide, copper, sodium bromide, sulfur dioxide, etc. Run down that list of substances and decide on the type of chemical bonding. Pause, come back, restart when you are ready to check your answers. Okay, so magnesium oxide is a metal and a non-metal. So that, of course, will be ionic. Copper is a metal, so that'll be metallic. Sodium bromide, well, that's metal and non-metal. Sulfur dioxide, those are two non-metals, so covalent. Hydrogen chloride, the same, two non-metals. And then an alloy, of course, contains metals only, so that would also be metallic. So moving on to covalent bonding diagrams. So covalent bonding is the idea of the sharing of a pair of electrons, outer shell electrons, of course, by two different atoms. So if we take a simple example here, hydrogen atoms combining to form the hydrogen molecule H2, and we draw our shell diagram for two hydrogen atoms. This is the nucleus, one electron in each of the atoms. Then they form a shared pair between the two nuclei. In doing that, we look at the left-hand hydrogen and say, well, that's got 2 electrons in its outer shell, which is the electron arrangement of helium, which is a stable arrangement. And we look at the right-hand hydrogen and we see, oh, that also has 2 electrons in its outer shell. It has a stable electron arrangement like that of helium. And of course, helium is a noble gas. It's totally unreactive. So this is our model for covalent bonding, the forming of shared pairs of electrons between atoms to achieve stable electron arrangements, that is, the electron arrangements of the noble gases. The hydrogen particle formed is called a simple or small molecule. So we use dot and cross diagrams to describe how the atoms are bonded together. Let's look at chlorine. We've got 2 chlorine atoms, both with 7 electrons in their outer shells, but we represent one atom as having its electrons as crosses and the other atom as having its electrons as dots. However, they are just electrons. Pause and draw the molecule, the covalently bonded molecule Cl2. Come back to check. Okay, so to resume, here is our chlorine molecule, ClCl. One shared pair, 2468 on the left-hand chlorine, 2468 on the right-hand chlorine. A noble gas structure like argon. Don't forget, chlorine has got 2, 8 as inner electron shells. Try hydrogen chloride. Draw the atoms and the combined covalently bonded molecule. Pause. Restart when you're ready. Okay, so 2 atoms, hydrogen and chlorine, and here is hydrogen chloride. 2 electrons in the outer shell of chlorine achieves the electron structure of helium. Okay, oxygen. Try oxygen O2. Pause. Come back when you are ready. Okay, so oxygen, a little bit more complicated. We've got 2, 4, 6 in the outer shells of each oxygen atom. To achieve 8, we need to have 2 shared pairs of electrons. So the left hand, oxygen 2, 4, 6, 8. The right hand, 2, 4, 6, 8. So we've got 2 shared pairs, and we would call that, of course, a double bond. So I'm going to give you some problems to try. Water, H2O, 2 hydrogen atoms and an oxygen atom. Pause and draw the correct covalently bonded molecule. Restart when you're ready. Okay, so we'll just have a quick look here. Here's oxygen with 2, 4, 6, 8. Single bonded to 2 hydrogens separately. So hydrogen achieves the electron structure of helium. Our oxygen achieves the electron structure of neon. 8 in its outer shell for oxygen, 2 in the outer shell for hydrogen. Okay, methane, CH4. Pause, come back when you're ready. Okay, so to reveal, here's methane. Carbon's got 4 electrons in its outer shell. 1, 2, 3, 4 covalent bonds with 4 separate hydrogens, 2, 4, 6, 8 in the outer shell of the carbon of methane. Try ammonia, NH3. Pause, come back to check when you are ready. Okay, here is ammonia. Ammonia, the central nitrogen has 5 electrons in its outer shell. 2, 3, 4, 5. So it forms 3 covalent bonds, forms 3 shared pairs with hydrogen each hydrogen achieving 2 in its outer shell. So nitrogen has an unbonded pair and then 3 shared bond pairs, making 8. Okay, here's a bit of a challenge. Try nitrogen N2 and carbon dioxide CO2. Come up with the dot and cross diagrams for those 2 molecules. Pause, come back when you're ready. Okay, so here is nitrogen. Nitrogen N2, each nitrogen atom has 5 electrons in its outer shell. The only way to achieve 8 is to form 3 shared pairs between the nitrogens, called, of course, a triple bond. I'm going to say, have you done the carbon dioxide? If not, pause, try it. Okay, so here is carbon dioxide. Carbon has 4 in its outer shell, oxygen has 6. A double bond, 2 shared pairs between the left-hand oxygen and the carbon, and 2 shared pairs between the right-hand oxygen and the carbon, making outer shells of 8 for each of the atoms. Covalent molecules are also shown in displayed diagrams, which show the shared electron pairs as a line. No other electrons are drawn, so just those involved in the bonding. So let's just look at one example. Chlorine, Cl2, very simple. There's one shared pair of electrons, so Cl line Cl. There is the displayed diagram for chlorine molecule. Pause and produce the diagrams for hydrogen chloride and oxygen. Come back to check. Okay, so to start, hydrogen and chlorine joined by a line. That's a shared pair of electrons. So one covalent bond. Then oxygen. If you recall, we've got 2 shared pairs of electrons between the oxygens. We did that earlier in the lesson. So that's a double bond, 2 lines. So here are some more covalent molecules that you've drawn earlier. Produce the line diagrams for these covalent molecules. Pause, come back when you're ready. Okay, so here's water, oxygen and 2 hydrogens, ammonia, nitrogen and 3 hydrogens, all single bonds, single covalent bonds, methane, you did earlier, carbon and 4 single carbon-hydrogen bonds. Nitrogen, if you recall, was a triple bond between the nitrogens, and carbon dioxide, oxygen double bond, carbon double bond, oxygen. Simple covalent molecules can also be represented as pictures or diagrams of the 3-dimensional models. So if we look here, here is a model which you may have met in the classroom. Propose, suggest a formula for this covalent molecule. Pause, come back to check. Okay, so generally we would have carbon and 4 hydrogens. 1 carbon, 1, 2, 3, 4 hydrogens, CH4. You may not have used those elements, but you must have a ratio 1 to 4. An alternative picture would be of this style. Pause, propose a formula for this molecule. Okay, so to check your answer, NH3 could be the formula. Nitrogen once, 1, 2, 3 hydrogens, NH3. Other elements would suffice. Simple or small molecular structure. So if we consider the molecules that we've met earlier in the lesson, the element hydrogen H2 forms a simple or small molecule. Methane, on the other hand, is a compound, but it also formed a simple or small molecule. So we need to define what we mean by the word molecule. It's more than one atom bonded together covalently. It can be an element, as in the case of hydrogen, 2 hydrogen atoms, or it could be a compound, methane, carbon and hydrogen, 2 different types of atom bonded together covalently. But they all are called or referred to as molecules. So, which of the following substances form simple molecules? From this list, select those that form simple molecules. Pause, come back to check. Okay, so let's have a look at the correct answers. Let's go through them one by one. Sodium chloride. Well, sodium is a metal, chlorine is a non-metal, so that would be ionic. It would form a giant ionic lattice. H2O, non-metal, so that would be covalently bonded and form a small or simple molecule. Al, well, that's a metal. It will form a giant metallic lattice. C2H6, if you haven't met it yet, that is called ethane. That is covalently bonded, non-metallic carbon, non-metallic hydrogen, so that would form a simple molecule. Magnesium oxide, well, metal and non-metal would be ionic, a giant ionic lattice. Finally, nitrogen, it's an element, but covalently bonded to form simple molecules. So imagine 4 methane molecules in a box. For methane molecules, you'll notice we've got carbon-hydrogen bonds holding the carbon and the hydrogens together, but there are no formal chemical bonds between the 4 methane molecules. So this is the distinction with the ionic lattice, the giant ionic lattice, the giant metallic lattice. As we will see later, or in a later lesson, the giant covalent lattice. There are no formal chemical bonds between the methane molecules. But simple small molecular substances do form solids and liquids at low temperatures. You know, water is a liquid at room temperature. You may have come across or seen in theatre dry ice, solid carbon dioxide. We know from particle theory that whilst there are no attractions between gas particles, solids and liquids are held together, or the particles are held together by attractions between the particles. So it must follow that there are weak attractions between simple small molecules. Otherwise, they wouldn't, even at very low temperatures, form liquids and solids. So chlorine, Cl2, whilst there's a strong chemical bond, covalent bond between the chlorine atoms, there are also weak attractions between the molecules that the atoms form. So we have Cl2, just some weak attractions between the two molecules. We call those attractions intermolecular forces, and you must use that term. These intermolecular forces are weak and are therefore easy to break or easy to overcome. Molecular properties. So the first property we'll look at is melting and boiling points. So consider the element hydrogen, H2, and the compounds carbon dioxide and water. What structure do these three substances have in common? Well, I'm hoping that you'll realize they are all simple or small molecular structures. What state do they have at room temperature? Pause and write down or think the state at room temperature. Okay, so methane is a gas. Water, of course, is a liquid at room temperature, and hydrogen is, of course, a gas. What sort of melting and boiling points do these substances have? You won't be sure, but write down a general idea of what you think the melting and boiling points of methane, water, and hydrogen are. Pause, come back to check against my ideas. Okay, so I've been a bit of a cheat. I've just said that methane has a very low melting and boiling point, as indeed does hydrogen. I think hydrogen's somewhere around minus 260, close to minus 270 for its melting and boiling points. Water, of course, I would expect you to know, or the exam boards will expect you to know. Water melting point 0 Celsius and 100 Celsius. So we can say in a general sense that small or simple molecular substances are generally liquids or gases at room temperature, or if they're not, then they would be low melting point solids. So we need an explanation for these low melting and boiling points. And that involves the idea that the intermolecular forces are broken in state changes for substances with simple molecular structures. Let's look at an example. Chlorine, which I have as a liquid, Cl2, and chlorine as a gas. In the liquid, the molecules are close together. In the gas, the molecules are spread out. But if we look at the displayed diagram in the liquid, we'll see we've got a covalent bond between two chlorine atoms, and in the gaseous state, a covalent bond between the two chlorine atoms. The covalent bonding is unchanged by a state change. We're simply changing the arrangement or distances apart of the molecules. The covalent bonding remains unchanged by a state change. It's the intermolecular forces between the molecules that, in this example, are broken. So if we look at the diagrams, the covalent bond remains unchanged. But in a liquid, the molecules are close together. In a gas, they're spread out. It's the intermolecular forces between the molecules in this example that have been broken. Because these forces are weak, these intermolecular forces, little energy is needed to break them, and the melting and boiling points of simple molecular substances are low. However, you may be asked to explain differences and trends in properties such as boiling points for simple molecular structure, for instance, in the boiling points of the halogens in group 7. So here are the halogens: fluorine, chlorine, bromine, iodine. Here is their molecular, or are their molecular formulae. I've filled in some relative molecular masses. Pause. Could you complete the relative molecular mass for chlorine, Cl2? Come back when you are ready. Okay, so the relative molecular mass of chlorine is 71. I will supply you with the boiling points. We have a boiling point of -188 for fluorine, -35 for chlorine, 59 for bromine, and 184 for iodine, molecular iodine. And if I graph those, we can see that there is a trend that relates the relative formula mass, or increases in relative formula mass, to increases in boiling point. So as the molecules become larger, the boiling point increases. As the molecules become larger, their relative formula mass increases, then the boiling point increases. That must mean that the intermolecular forces between the molecules increases. So this is the principle to take away. As the relative formula mass increases, the intermolecular forces increases. That means the boiling points increase because more energy is required to overcome the stronger intermolecular forces for larger molecules, and less energy is needed to overcome the intermolecular forces for smaller molecules. Let's consider the second key property of simple molecular substances, that is their non-conductance. If a small molecular solid is heated to its melting point, a liquid forms. So we would represent that in particle theory as particles fixed in positions in a regular arrangement for the solid, to particles that are free to move, small molecules that are free to move and that are more randomly arranged. But as the molecules do not have an overall electric charge, that is, they have as many protons as they do electrons, so they are electrically neutral. As the molecules do not have an overall electrical charge, their movement cannot produce a flow of charge, an electrical current. Small molecular substances are non-conductors. They do not conduct in the molten state. Ionic compounds, I just may remind you for comparison, do not conduct as solids, but do conduct in the liquid state. Their ions are free to move, the ions carry charge. However, a covalent molecular substance, particles may be in a fixed regular arrangement in the solid, but they, in the liquid state, are not able to produce a flow of charge because the molecules do not have an overall electric charge. Therefore, small molecular substances are non-conductors as solids, liquids, and in solution if they do dissolve. And finally, the limitations of the covalent models described. There are many limitations to the models that we use for covalent bonding at GCSE. You'll see textbooks list extensively, but here are three of the most central. The first is that they models that we're using, the dot and cross diagrams, the displayed diagrams, the ball and stick, do not reflect the relative size of the atoms involved. The distances between the atoms in the diagrams are far too large. The molecules that we draw are in 2 dimensions rather than representing 3-dimensional shapes, which is something that you'd meet at A level. So you now need to practice. I suggest you first of all do the textbook end of chapter questions, for which you probably can find answers, and then move on to past paper questions from the particular exam board that you are taking. If you don't have immediate access to those, there's a website, Maths and Physics Tutor, which has collections of past papers and answers by exam board.